physics time. That was in the back row during the last few minutes of Cosmology lecture. And I was just wishing that maybe if it were like 12 years earlier, I could be an undergrad. I could sit there and someone teach me answers. That would have been really fun, right? So because I start with this because uh, I want to part my cup with a little anecdote, uh, just to get engaged. So about cancers. So as an undergrad, we didn't really have much at BRAC University. So BRAC University soon, right? So we were like 2, 3 people in the physical side. So we barely had a classroom or so. Um, so there were no cancers, there were no nothing, right? So just the bare minimum to get a physics degree. But so when I went to grad school, my first class was classical mechanics, and the professor, he was later on my thesis committee. He was species cancer, the first year of class, and he had started with nectar cancer and all of it. And I was just kind of blank, like what about it all? He's right. He righty vectored that one index cancers, and all I know about is that it has magnitude and direction. So that's my level, and we talk like this. So and I see everyone around me writing notes and taking notes, asking questions. Oh, I don't handle the dumbest person all that. Um, so then I get up the courage and ask a question. So okay, sorry for asking the dumb question, but what is a tensor? You know what it is? It says tensor is a tensor is a something that depends on like. See the problem with that? Only a physicist will make that definition. But okay, after attending her class, you probably know what a tensor is. So good for you.
All right. Now, where's that pointer?
Okay, all right, good. Now we finished here, right? So what did we have? Well, we defined the scalar field, and it acted on the ground state and gave you a sacred some momentum. So basically, whenever this field acts on the ground state, it gives you a particle, right? It creates a particle. All right. So that means basically built in it. This is defined in terms of ladder operator creation and analysis. So it can create particles, it can prepare particles as well. Uh, Slides are not changing.
That's your point. No. Now, um, we want to start with the causal structure of quantum field theory today. So we talked about causality yesterday, and so causality is important whenever you have special relativity theory. Quantum field theory is nothing but the marriage of quantum mechanics and special relativity. So causality is going to be a pretty big thing. But let's talk about causality. So you have this inner here. This is basically an amplitude. So what does this be? This bracket notation with pi x and pi y. Well, this means that this field right here acts on the ground state, creates the particle at y, and then this acts on this one, disperse that particle at x. So this is what it means. So you start off with at some point, right? And then you kind of transition to x, and we call this thing the propagator. Okay, so this expression right here is the expression of this line going from y to x. So this is going to be like you're traveling from y to x. So this is the propagator, right? And it's signified denoted with the d. And the commutative relationship for this goes like we define about commutator, right? And we can write this in terms of the t, your propagator. So you see you have two propagator. One is the propagator x from y to x, which is this one. And one is the propagator, which is x to y, the other way around, right? So we want to see, is it that key, this will measure the same thing at this one? That's going to be the question that's going to determine if your theory is plausible or not. So what I mean is, if this sums to 0, then your theory should be causal.
because the order of measurement in that case should not matter. Okay, if you have periods also. And then let's define the propagator in terms of the intervals like we defined in the previous class. So I just quoting it off. So essentially, you have, remember what dx minus dy was? This is this thing. So this acting on 0 gives you this thing right here. And this thing acts on the browse curve gives you this thing right here. Right? So you have 2 0 and you have one on broad state and I guess x state, right? Like the adjoint. And so I can hate everything now. Really, all of these things I can take out. And all I'm left with is this complicated looking big expression right here, right? There are 2 integrals in x, you have all these factors of x, and so ultimately you have inner product t and p prime. So these are 2 different states, right? And we know that p forms the complete self state. So this must normalize. So then this is nothing but the delta function, right? With some constants that kind of guarantees Lorentz invariance. And then you have the 3-dimensional delta function. All right. So then the delta function you integrate over that sets p. So this should be p prime actually, not q. So basically the delta function integrates out and sets p to q or p to p prime, sets them equal to each other. So ultimately you get everything that's p prime looking somewhere here goes to p. So you get this simplified expression. So this is now your propagate. Okay. So then what does this give me? This p dot x minus y. So what is x minus y here? Well, it's x minus y squared, the distance between the squared, is less than 0. This is the Lorentz invariant proposition. The distance squared can be greater than 0, can be less than 0, can be equal to 0. Where this is less than 0, right? Then we have a space like kind of situation, right? Remember causality from yesterday, like cones and stuff. We have a space-like situation in that way. If you have a space-like situation, remember what that is? Well, 2 points in space-time. One is inside your light bulb, the other is outside of your light bulb. So one cannot affect the other. So it should not matter whether you are doing the measurement inside the light bulb first or outside the light bulb, because if the particle can go this way, it can, with same lightness, go the other way because they're not positively aligned. So then, if you have space-like situation, causality should be mod that this goes to 0, but it doesn't go to 0. It decays exponentially outside the light bulb. So this is alarming, really, because then that means that you can go beyond speed of light and take part in these space-like situations, which is alarming. But the situation really is alarming, but not unsolvable because you have an exponential decay. So it's not 0, but it's going to decay exponentially. All right. So then causality requires this commutator to be 0, that means the order of measurement by x, by y is not matter, right? So this is set to 0 by enforced to 0 so that, you have a causal theory. Okay. But this will have some kind of consequence. And to protect this causality, to ensure that this actually is 0, we use the Feynman propagators. The Feynman propagators just use this propagator, but with a factor of t here. This factor of t is known as time ordering. So we learned about normal ordering yesterday, like the annihilation operators, orders to the right, and then the accretion operators and whatnot. This time ordering just means the earliest field is going to be to the right. So this is basically going to protect your the causality of theory. So basically, the propagator can be 2 kinds. One is when phi xi when the x0 is greater than y0, and otherwise it can be phi y phi when x0 is less y0, right? So basically, a piecewise function of the propagator. And to my math physics too, what does this look like? Piecewise function of propagator. So this is going to be the Green's function.
So this is known as a time-ordered propagator or Feynman propagator. Okay. All right, good. Now, let's move to a complex scalar field. The complex scalar field, so far we have only got about real scalar. The real scalar field only has 1 degree of freedom. What does that mean at a quantum level? 1 degree of freedom just be any excitation of your scalar field will give you one kind of particle, right? A spin zero particle, if you like, to take boson, for example. However, if you have a complex scalar field, you automatically have more degrees of freedom, right? You automatically have, let's say, 4 degrees of freedom because you have phi and phi star. Phi has 2 components, real and imaginary. Phi star has 2 components, real and imaginary. So 4 degrees of freedom. And then you have 4 complex degrees of freedom, but then you have 8 real degrees of freedom. Imaginary part is just I times up real part. So you have a lot of degrees of freedom, but at a quantum level, what time points down to says to complex scalar tree can give rise to two particles. One is the particle itself, and what is the other one? The antiparticle. So that's where Jamal came up with this antiparticle business, right? And the negative energy, negative kind of propagator that we found actually turned out the propagator for the antiparticle going. We say the antiparticle goes back in time just to make it analogous to a particle, but it doesn't really go back in time to work on that stuff. All right, now complex scalar field. So you consider this Lagrangian. So again, I gave you a Lagrangian. I handed you a Lagrangian for the real scalar field. I'm doing the same for the complex scalar field. And you see automatically the Lagrangian look little more complicated, right? So instead of having d square or d phi, you just have now d phi star and d phi. So effectively, you can treat phi and phi star to be 2 independent fields, okay, to do this problem. And this is, as usual, the mass star. So then the kinetic term is the mass star, and then this is basically how we define a complex scalar field of Lagrangian. And so it has 2 independent degrees of freedom, meaning it has 2 independent fields, phi at phi star, right? And phi x is defined by this ladder operators. It's not different than what we did for scalar field. In scalar field, we use the creation and annihilation operators A and A dagger, right? Or A dagger and A, respectively. But here we have, for phi, we have chosen both B and C dagger. And for phi star, then these are just complex conjugate, right? Because this is a complex conjugate of phi. This becomes a minus, this becomes, that's all it is. And this becomes dagger, this becomes a null C. So this is what you have, how do you find your fields in this theory? And then the conjugators are very similar to what you had before. The B and B daggers and C and C daggers will commute whenever P and Q or P and E prime. I think I'm missing some primes here, forgive me. But regardless, whenever you have P and Q not equal, then they commute. Otherwise, they don't go, right? Otherwise, the order of measure is important. All right. So what do they do really? Well, the B's and C's will annihilate 2 different types of particles. So you choose 2 different kind of annihilation operators, B and C, because you'll have 2 different types of particles. So one annihilation operator cannot really destroy another kind of, so it only assigned to specific. Okay. So then the role of the C daggers and D daggers would then be to create new particles, new different particles, right? So it turns out that the complex scalar field has internal symmetry. So symmetry by definition means something happens to the system and the system doesn't shift. That's very improved manner. That's how we put the symmetry. Internal U1 symmetry just means that if you shift your field phi by some exponential e to the I alpha times the phi, and you plot this change into your Lagrangian, the Lagrangian stays same. Right? So that means this is the U1 internal symmetry of the complex scalar field theory. So if you have this shift for the phi, then you will have a conjugated shift for the phi star itself. And If you put these into your Lagrangian, then there is no change in the Lagrangian symmetry. Okay, and this will play a big role when we set up QED or quantum electrodynamics. But we have to do something else to this E1 symmetry. We have to promote it to a Cage symmetry, but we'll talk about that later on, correct? And then we talk about Noether's theorem, and Noether's theorem just implies that for every continuous symmetry, you would have a conserved star, right? And it turned out for this U1 symmetry, the conserved stars is this thing right here. So Q is, so whenever I'm talking about charge, it's often mistaken to be always talking about electric charge if you're not initiated to these weird kind of things that we call quantum field theory. But this is not electric charge. This is basically a charge is something that is just property that is conserved. Yeah, that's it. It's a charge can be one of those conserved quantities turns out to be electric charge, or that's that we charge. Okay, so you're denoting Q, but don't mistake it for a electric charge. This NC just means nether current or nether charge, whatever you like. So the nether charge or the nether charge is this quantity here. But what is this quantity? Well, it's integral over some momentum space, the total momentum space, and it's basically a sum over some n's. What are these n's? Well, these n's are nothing but products of these and d layers, basically the annihilation operators for the B kind of particle and the creation operators for the B kind of particles. And these are n just define the number of particles that is created by this B diagram. Okay. And then similarly in PC just denotes the number of nth part created by the C diagram. Okay. So this is why you separate NP and NP. Basically B's give rise to particles, C's give rise to antiparticles. So for a complex state of field, now you have two things coming up. You have the particle, and then you also have the antiparticle. So you need two different operators to create particles and antiparticles. So this, the product of B's acting on some state will create only particle. The product of C's will create antiparticles. Okay? So, sorry. Yes. Oh, well, because you keep acting P's, Dirac found that it gets to negative energy. Energy is bounded, but not bounded below. Yes. So then it was interpreted to be just B antiparticle. So charge is really conserved, really. It antiparticles in B. All right. So this is quite an important discovery. All right.
Yeah. One question was asked. So far, any other question? Yeah.
Reference? Currently, I'm taking from a lot of different things. But at the end, I will give you a set of references. You can read from like yesterday, you can go through South Western and what, or also follow from top. David on both is pretty good. Any other questions? Yeah. So well, the propagator is the product of like fees, right? Basically, some order. No, the propagator is basically a scattering amplitude. So it's operator acting on some state, but then you close the state on the other side. Basically, at a transition amplitude of the particle going from one place to the other. Symmetry has to be local. This is just U1 symmetry. You just shift the fields. So what I mean, okay, good question. So what I mean is that a gauge symmetry, whatever, but a gauge symmetry will have this parameter alpha dependent on every space sample position. This is just the global symmetry. Okay, so this doesn't care where you are in space. You can be anywhere, but the Lagrangian will satisfy this symmetry. But we turned out, I won't tell you what turns out. We have to wait for later lecture. But okay, it is not a big thing. Okay? Well, okay, we can, I guess, move on. Now, so far, what we have done is we have only talked about a very special case of quantum field theory. We have only talked about the free quantum field theory. By free, I mean it's free, literally free. It doesn't interact with anything else. So basically, your Lagrangian, you have the kinetic term for the fields, and you have the mass term for the field. But the fields itself, there was no interchange. So what I mean by that, so if you have a plus b whole squared, right? That's a mathematical formula from elementary school. And you have a squared plus b squared. Those are the terms of the free field. A by itself, b by itself. A is the kinetic term, b is the let's say the potential term. But then in the middle term, you have 2ab. This 2ab is the mixing of the two different things, a and b. We didn't add those in our class. Now this include interaction, right? So when fields talk to one another in this kind of an interaction, we have what we call interaction. So without interaction, we wouldn't be even, right? So this interaction business is what really makes quantum field theory a money maker. No, it doesn't make you any money. Right? It should though. Introduce you turn to the Lagrangian to incorporate interaction. So we had this Lagrangian anyway. We have seen this Lagrangian before. That's fine. Now incorporate term. So these terms you see phi cubed. What does that mean? Well, that means there are 3 phi's at the same position. So basically, a conversation between 3 fields. So 3 fields that interact. Here we have 4 fields. So this is 4. And where are these lambda? These are parameters that will vary off we were. And dimensionally speaking, this protects the dimensionality of the field. Remember your Lagrangian, our dimensional analysis from the very first few minutes of yesterday's class. Dimensions are a very important thing for consistency in physics, right? So one is the dimension of a Lagrangian. That is going to be the key question whenever you set up interacting field. Because every term in the theory you're adding needs to have the same dimension. You cannot ever add an apple to an orange, right? You can always compare an apple to an apple, but you can never compare apple to an orange. So whenever you're adding term, their units must be consistent. They must all have the same. Yeah. Oh, and this why failure. Really, these are the sheets. Yeah, and we're not exciting. These are very boring. They're not excited. All right. So these are called self-interaction curve. Okay, self-interaction. There's a name to this. Interacting with self. So phi to phi, and so on and so forth. So which terms are allowed? That's one question that I was posing, right? And it turns out you can do some simple dimensional analysis. And remember that the action has dimensions of h bar, but non-natural units, h bar has been set to 1. So basically, it turns out that in non-natural units, the action has no unit. So, right, it's dimensional. So that means whatever Lagrangian you have must kind of, from the Lagrangian, you find the action. A change in the Lagrangian, you have the action. So action to be dimensionless, then that integral must be dimensional. So that turns out either is that you have action integral over this big thing. We know the Lagrangian, we know the action as dimension of 1, which is basically unityless or dimensionless. So how does this integral support this fact? The only way it can do it is you have d4x having dimensions of -4, mass dimensions of -4, because Lagrangian has mass. Okay, how do I know that? Well, you just look at this term in the Lagrangian. This has two mass dimensions, m squared, and every phi, it's a scalar field. Okay, we're going back to real scalar fields. Every phi has 1 degree of freedom. So you have 1 mass unit, another mass unit. So in total, you have 4 mass units. So then every term the Lagrangian must have dimension 4 mass. All right. So that means any
interval measure must have the inverse 4 dimensions. So the sum to 1. Okay? So basically, this unique consistency demands and protects this dimensionless action, and we say Lagrangian has dimension of 4. Right? So then every term must have the same mass dimension. Every term that we cube in Lagrangian must have mass dimension of 4. So then phi must then have, because to build the Lagrangian of mass dimension 4, phi at dimension of 1, every real seriously has 1 with D of real. So then phi cube will have 3 mass dimensions. Then you have 1 mass dimension remaining, because every guy with the Lagrangian must have 4 maximum. So then in here, lambda will be mass dimension 1. If you go to the next term, pi 4, then pi 4 already has mass dimension of 4. Then in this case, lambda 4 has no dimension at all. If you go to the next term, then you have to include the correction as well, because then you have lambda phi, phi, phi. But phi does mass dimension of 5, but the term in the Lagrangian must have mass dimension of 4. So you kind of have to cancel out the 1. And how do you do that? You basically divide this term by cut-off energy. We're cutting off our theory at some energy level, and that energy has mass. So if you protect your dimensions, so it turns out that any factor of lambda that you plug in must be a function of energy or mass, because they have the same units. And these, by definition, are weaker than these terms, in the sense that these lambda parameters that include are only so much smaller than 1. And we call these things perturbations. You're disturbing the sea. Right. So how long do you use physics in this realm? Well, physics starts by setting up the Lagrangian. So when your friend discusses physics, you hand your friend a Lagrangian, and he writes down a Lagrangian with all consistent terms. By consistency, I mean all of these terms must first obey that every term in the Lagrangian must have mass dimension 4. If it doesn't, then your Lagrangian is useless. It does not work. Okay? And then you cut off your Lagrangian wherever you want, depending on how much precision you want. All right? So let's say I want to cut off my Lagrangian here. I have a 5-4 theory or something like that. But if you want to go higher, that means you're basically compensating for that dimensional analysis. So you're cutting off your theory at some high energy lambda, right? So this is where the current effective field theory comes from. You cut off your theory because quantitative theory cannot be valid to all energy field, as we had talked about yesterday. So we cut off our theory wherever we want, depending on the amount of consistency or the amount of precision we demand from our application. Right. So one alert I should have mentioned when I said 5-4 theory. So 5-4 theory is what we're going to discuss now. So 5-4 theory is where you have a Lagrangian with this interacting term. So you have a 5-4 term, and this is now dimensionless. So this is all the 5-4 theory. Okay? And any kind of interaction basically sets up a potential. So you have this free Lagrangian, which has the kinetic term and its free potential, but then you have a perturbed potential due to the 5-4 term. Okay, so you can derive the equations of motion, the order and the Lagrangian equations, and you'll find that, okay, for the free field, you have this, no problem at all. And the remaining part, due to V, it's just going to be the partial derivative you expect part. You can easily work it out on our own time. It's not that hard. And you take the derivative of this term, simplify to get 1/3 factorial by the 3 times lambda, right? And now phi to the 3 can be expanded. If you say, okay, phi is being perturbed by lambda, then you expand in terms of this lambda thing, and you spend phi. But what does that mean? Well, it means you have the free field, and then you have the phi 1, then you have phi 2 multiplied with another lambda, and so on and so forth. And this term is as a whole. These are all encoding any kind of disturbances in your field. So to pictorially see what that means, your phi 0, let's say it's a Gaussian, right? Let's say it's a Gaussian, and it looks like this. It looks very nice, like a normal distribution. So this is the free field, right? But when you perturb this free field, it's not going to be so nice, or it's not going to be a be it's going to be kind of a frown. You perturb the field and you get some small spikes here, right? And you have a frown instead of a set. So this is what it means to perturb your field. You kind of disturb it so that it kind of waves a little bit more. Okay. And then what does this mean to be interacting? Well, interaction just means how many terms in my derivative? You have 3 phi's. So basically 3 phi's are kind of interacting, but the quash. Three. So via this phi s. But what is this phi s? Well, phi 0 basically interacting with, so if all of these pi 0, 3 factors of phi's, basically are talking to one another at this point right here. But then something has to mediate that communication. And that communication is mediated by this phi s. And again, I'm really pushing my lab physics students to answer questions for me. What does this look like? So let me just give you a brief review or kind of an int. Forget about this star. This is just a constant. And you have this integral, and this is solution. So if you have this as a solution, I1 is your solution because, I'm perturbing in by 1 term. I'm looking at this term now. If this is your solution, then to find that solution, you want to integrate over the space, and then you find the response to this interaction. This is the response to this interaction. What is the response to this interaction? So this is the green option, right? So this is the propagator. And this propagator basically tells me, okay, I'll mediate this interaction at this point. If I have this, so I perturb this field at some point, that perturbation is mediated by this green function propagator to that point where the three things interact. Okay, so this is a skeleton, a very bad skeleton of a Feynman diagram. Okay, so this is a green circle that mediates, the propagator that mediates this interaction. Okay, so phi of S is then the green circle, right? Okay, now in a quantum theory setting, what does this all mean? So this is still in the classical realm. In the quantum theory setting, you have this phi 4 term, and what you do is expand phi 4 in terms of A greater than A, right? Because every pi is defined in terms of creation and analysis and operators. You kind of can expand it. So basically, you have 4 factors of phi. You get terms like these 4 factors of 4 products split. Products of 4 terms of A daggers or A daggers at 1A, whatnot. You can get a lot of things, right? So basically, what that means, sometimes you'll be creating something, sometimes you'll be destroying something, right? So that is where the term, that particle number is violated in quantum theory comes from. So you have 2 particles starting, collide at high energy, and then a lot of stuff jumps up. Particle number is definitely not conserved. And one of the motivations of building a quantum field theory was to account for that. Okay? And a very simple analysis of quantum field theory just leads to this fact very easily. Somewhere you create particles and somewhere you destroy particles, and you can start with some particles, but you end up with a lot of more or a lot less. That's another, right? So definitely, phi 4 theory, particle number is that not uncertain. All right, now we talk about interaction. A thing that describes interaction is the S matrix. What does the S stand for? S stands for scattering. So interactions means the coming together of let's say 2 particles for simplicity, and they scatter off one another, right? So then to describe this scattering process, this terms interaction, you need a matrix, because we love matrices. So S matrix is the scattering rate that describes the part of scattering process, which may look like basically you have 2 things coming together, exploding into a bunch of other stuff. And then at the end of the process, 2 things may go apart, right? Fly apart. So this is quite simple. The 2 particles coming together. How bad can it be? This is also quite simple. 2 particles going far apart. Far apart, I mean very, very far apart, so that there is no interaction we can. Here again, no interaction we can assume that this in this situation. But here, it's the complicated real world that it's in, right? So this is quite messy, as the cartoon shows. And we had John Wheeler to thank for how he deal with this messy. So his recipe was you split the Hamiltonian. The Hamiltonian is what describes quantum system, the energy of quantum systems. And you split the Hamiltonian into the simple parts and into a complicated part. So this is a free Hamiltonian, no interaction at all. And then this one is then the perturbed Hamiltonian. And you define non-interacting states at these locations, and non-interaction states can be denoted by a side, and it basically encodes the momentum. So it encodes the momentum of P1. Let's say this is P1, and let's say this is P2. So they're coming in. So we can write it as P1 and P2 going towards one. And you also have a phi that describes the outgoing process, which I'm denoting the outgoing moment as P1 and P2. All right. So this is a real shape, but it's a simple enough real shape that we can say, okay, like no interactions at all. And this is also a real state, but this is also quite simple. So we can just write when we want the two moments separate. So this is, we can assume that happens somewhere way before collision, like at T negative infinity. And this is somewhere way after scattering the process. It's at T to both sides. And then you define the amplitude. So what is the scattering amplitude? How strong? How big is the number? This complicated real world with. All right. So the amplitude is defined as you have an outgoing state, right? Something comes in, something goes out. So this is the inner part. You're going from psi to phi. So to go from psi to phi, something messy happens, and that messy phase is encoded by the S. Then you plug in the S inside and repeat. So these are matricially. Right? So you have T1 and P2, the incoming momentum, and then these are operated on by the S operator and gives you the alternate states. But this is how you define your amplitude. This is the S matrix. And every one of these is the S matrix itself. We have a big chunk of matrix, each element given by that. So what is the structure of S? Well, what is S doing? So you have to put something in to begin the operation. It turns out you have to really, so how many pictures of quantum mechanics there are? 3, right? So one is a Schrodinger picture. In the Schrodinger picture, the state vectors are time dependent, but the operators are time independent. Then you have a Heisenberg picture, which kind of splits the notion around. You have the operators that are not time dependent, but the state vectors are not. And then you have a third picture, which is the interaction. And that is the most useful when describing interaction processes and S matrix processes. And it turns out the interaction picture is kind of a marriage between Schrodinger picture and Heisenberg. So in the sense that both state vectors and operators are now time. So if you do that, basically what happens is in the interaction picture, S turns out to be the time evolution operator. And if you have the time evolution operator in between, and you have a lot of pi's and pi daggers and A's and A daggers in there, these can get a lot messy. You can have pages of calculation. You go to grad school, you go on the P3 course, you have pages of calculation. That's work. You do it at 4 a.m. in the morning. And that's how you learn, right? So you put in the hard work. And in no, they become time. So you have to put the time dependency as well. Yes. So that's a lot of calculation, people. But yes, good point. So you have to make everything time use. And what on the after the mess stops so that you have reduced your S operator to be just the random S operator. But that has to take effect on the dependence of time on the input. Okay, so yeah. So this becomes very messy. There are a lot of things to calculate. This becomes very messy. A lot of matrix amplitudes to calibrate. Some very max. But thankfully, we have one brilliant mind that has done things down for us. That is Richard Fein. So as Julian Schreier puts it, like the silicon chips of more recent years, a final diagram was pretty computation to the masses. So any idiot like me can do final diagram. So, if I can do it, better I'll get them. So yeah, Julian Schreier, who's one of the Nobel Prize winners, we find he has this big big thing to say about final diagram. So S matrix calculations without final diagrams are quite tedious, and you would not need 6 lectures, maybe maybe 10 lectures that to help with one. So that's not going to be very helpful. So thankfully, the world had found the brilliance of this method. So saying, and so we see what a Feynman diagram is for the first time. So this is another skeleton of what a Feynman diagram may look like. So you have a scalar field end up going into a blob. That blob is just some source interaction. So this is some source that is kind of disturbing the field or something. So the field on this and interacts here. So that is what very basic Feynman diagram. Then you can have the phi-4 theory. You have talked about this just now. You have 4 fields coming in at one single point and interact. So this is another Feynman diagram. Now for the phi-4 theory. And the phi-4 theory is the interaction Hamiltonian that you have 4 fields at one vertex. And then you have this kind of an interaction which has psi daggers and psis. Usually you denote spinors with it. But for now, let's say these are just complex valued scalar fields. So complex scalar psi with real scalar phi. This interaction is basically this vertex. At this vertex, complex scalar comes in, real scalar comes in, and a complex anti-scalar or conjugate scalar kind of comes in as well. But you notice the arrows and they will play a big part. So coming in is denoted of that. Adjoint psi is given with the opposite arrow. And that has some meaning. We'll talk about that meaning. So, but this is another 3-level Feynman diagram. And this is the Hamiltonian interaction looking like it. You have psi dagger, you have a psi, and you have a phi. So basically, you have essentially 3 fields interact, 3 types of field: psi dagger, psi, and phi. So does anyone know the name of this kind of an interaction? This is probably. So this is not a spinor, but yeah, I see where you're going. At this point, this is just scalar, complex scalar. But this has a name. Ikawa interaction, right? After Ikawa. All right. So then the most important kind of final diagram is this. And this is where we get light from, really. You have a scattering of 2 spinors, positron and an electron or something like that. And they interact, but they talk to each other by the language of the photon. And that photon is encoded by this wavy line right here. And electron comes in, positron comes in, emits a photon, and then goes away in their separate directions. That is a very important Feynman diagram in the way nature works. And this is basically encoding quantum electrodynamics. Okay? So basically, it's merging Maxwell's theory with the quantum theory. So I like this diagram so much, right? And this diagram kind of basically equals the Coulomb interaction and has this complicated looking Hamiltonian. But all that said is that the interaction between the photon field, which is this vector field right here, the size and side anchors. But I love this diagram so much that I bought a t-shirt when I was in grad school. So when you're in grad school, you don't have much money, right? And basically, you buy one t-shirt, you wear it every day for one semester. I used to wear this t-shirt every day for one semester. And it also, like the bank period was a big thing when I was under rep, and Sheldon used to wear these kinds of t-shirts. And I'm not as smart as Sheldon, but does it hurt to pretend? Then you get a lot of attention from people like, oh, you find a diagram on there. So even people who don't know physics, you find that. So you got a lot of attention. And so I bought this t-shirt, right? Exact t-shirt from Amazon. And I used to wear it so much that my wife is not there. And she's a faculty here as well. And she's a cartoonist, He drew a cartoon of A and her. And you can see a Feynman diagram. It in. Yeah. So this is what she drew, and I love this so much. Then I made my. Okay. All right. Good. Some entertainment. All right. Now, let's actually do some calculation. So let's do a toy model calculation of the Feynman group, right? So how much time?
So let's do some calculations of the final moves using a time, right? Okay. So imagine we live in a world of three scalar fields, right? So we have nothing else. It's a very boring world. We have three scalar fields. But do you see the conundrum that a world described by three scalar fields only? Do you exist in that world? Of course not. We are made of matter. Matter is made of kernel, electrons, protons, blah. We don't exist. So there is no point of that. But you're going to do it anyway because we're crazy. Right? So let's do a three world scalar thing. So we have three scalars that describe the world. We have A, B, and C, let's call them. And usually, for correctness, scalars are denoted by dashed lines. These are solid lines, but we're doing a coin query. So who worries about that? Anyway, so you have three scalars interacting at this location, right? And time goes to the right. So time goes forward this way. So time going forward this way just means something is propagated from this point, that interaction happens here, and EHC goes away, more time. So these lines are external lines, and these are basically encoding that something is moving from here to there, so it's an external moment. So where does this come from? Well, here we encode the final real that we're doing quantum field theory, but the excitation of the fields, we are creating particles, the next particles. So again, we're back to the picture of the very old picture of particle interaction, right? So he kind of defined these particle interactions using finite time. So assume that A has more mass than B and C, right? So that just means A can decay to B and C, right? So you can have a lot of different Feynman diagrams with different loops internally. So that just means you look at the first diagram, you have A going to a T first and then a B. Well, that means A is decaying to both of these B and C because A is bigger than the sum of both of them. So that is possible. And then this is another line that can happen. C and BD can talk to one another again for some other interaction mediated by A. And then finally, you have B and C coming out of this. So this is what we call a triangle diagram, triangular part. You can also have a vacuum self-interaction diagram, but this is not self-interaction, but it's just a vacuum like with this bubble in here. And you can have a lot more. So these are external lines. A's, the outer B's, and the outer C, these are called external moments. But then you have these eternal things, the eternal line, the eternal loop. These are called eternal moments. So there are two kinds of momenta in ion that. The external momenta and the eternal momenta. The external momenta are the momenta for the particles that we actually see. These are real particles. The eternal, anything goes. There is no set. Unless it's absolutely forbidden, everything is possible. So internally, you don't care if you have a tachyon or something, but theoretically, it's anything works. Eternally, because we don't really measure eternal particles. Okay. So we have a scattering process that looks like this. So remember, time goes this way. So basically, these two A's are at the same time. So A comes in, A comes in. So you have two vertices, one vertex here, one vertex here. So essentially, these two need to talk, and they talk via this mediator that we call C. This is then the propagation, right? So they propagate this interaction to A, and two B's come. So basically, two A's scatter off to two B's. So this is a scattering process, or this may be a scattering process. Two A's, the A's and B's may talk, a mediator C, and then a scatter off to A and B. Or you can just split the diagram, you get this kind of a figure, right? So you can do a lot of things. Actually, you can draw a BC order by for any cluster. There is infinite amount of number of Feynman diagrams that you can draw. So a generic Feynman diagram is that a lot of momenta comes in and a lot of momenta goes out. A blob just means anything goes. A lot of interaction. Okay. So let's do some math. Let's calculate Feynman diagram. So the first, to actually put it in practice, we need to know Feynman rules. What are the rules to draw these diagrams? Because we can't just
squiggly lines and get away with it, because we are not finding. So Final's recipe for calculating these diagrams is that first there's some location data. You label incoming and outgoing for momenta as P1, P2, P3, and what cost in amount of momenta, internal momenta that is. And you label the external moment as Q, P1, Q2, up to Q. Then you go look at how many vertex vertices you have. For each vertex, put in a factor of minus I, G. I is a coordinate number, and G is the coupling constant. The coupling constant, I mean how strong the interaction is, right? So basically, in our toy model that we're going to study, this coupling constant will add dimensions of momenta. However, in the real world, the coupling constants are dimensional. Okay, but this is a prime model. We don't live in a prime model universe. Okay. Now we have the propagators. That means each internal line. So for each internal line, you write down a factor of I over Qj squared minus Mj squared. It's not completely correct if you're done real theory, because Feynman gives us a prescription to do real theory by adding some I epsilon that we define contour integrations. But that's what something like that. You do a whole course on completely for that. The energy momentum conservation is accounted for. So I was listening to that Holography GR, and energy is not conserved. But in particle physics world, it's always conserved. Okay, so to account for energy momentum conservation, for each vertex, you write down delta function, and the delta function looks like this. Okay, so for each vertex, you have this factor and also this factor. This accounts for the energy momentum conservation, because look at the signs. So these are all pluses, but they can be pluses and minuses. So plus can be something coming in, momenta coming into the vertex. Minus can mean momenta going out. So plus and minus sounds delta. So that accounts for your momentum conservation. Also energy, because we're talking about 4 momenta. The zero component is energy. The IF component is 3 momenta. And then you integrate over the internal momentum. So basically, you sum over all of the internal momenta that you have by including this factor over the internal momenta Uj. These factors of 2 pi in the fourth, 2 pi to the fourth, come out as a consequence of Fourier transform that we did yesterday. And Feynman tells you that if you can't keep track of your 2 pi's over 4, might as well not keep physics at all. So I want to keep track of it. So erase. So after doing all of this business, you will find one delta function remaining. So what you do, Feynman tells you just erase. Just erase it. So you just erase your delta function, and to account for the erasing, you just multiply your answer by that would be the amplitude of your semi process. So let's do a problem. So we want to calculate the amplitude for this scattering process. A scatters within A to give you a peak as C. So you have 2 vertices. A comes in, talks to a kind of B over the vertex, like it may be a B, doesn't matter. But okay, it talks with a C, and then D and V comes out. That should be so. All right. So then, first to Feynman tells me is label the external moment by P. So I'm labeling it randomly. So this symbolic P1, this symbolic P3, this symbolic P4. Okay. So they're done. Then label your internal momenta. There is only one internal line. These are all external. This is one internal line. So you have one internal momenta, Q. And they what? Well, basically we're done with the notation. And then we started to refactor. So how many vertices we have? We have 1 and 2. So we have 2 vertices here. So we have 2 factors of minus Ig. So we square it. And we have 1 propagator. So for 1 propagator, you have I over Q squared minus MC squared, the mass of that propagator. Okay. So you include that. Okay. Then you watch. Well, for each vertex, you account for energy momentum conservation by including delta hub. You have 1 and 2. So you need 2 delta functions. So one is for this vertex. At this vertex, we're at P1 comes in, Q goes out, and P3 goes up. So you have the delta up. So P1 minus H minus Q. So those who are familiar with Kirchhoff's laws of statistics. He was doing particle physics without doing particle. His case here is basically current pumping, current goes up. But yeah, he's not as smart as Mike. Any. All right. Then you have another delta, which is this, that part, X. So P2 comes in, Q comes in, P4 goes out. So you have P2 plus Q minus 4. And you have factors up to pi because Feynman tells us QB and if you transfer to pi. And then all you're left remaining to do is integrate over this internal momentum, which is d4 to q over 2 pi to the 4th q in k. Okay, now this looks complicated, but it's really not because the integral is over q and the delta function of the k. Integrating delta function is probably are the most trivial integrals that you'll ever do in your life, right? So basically, you choose any one delta function to get rid of. So let me choose this. So remember, integrating over delta function gives you 1. If you have some function multiplied with delta function under the equal sign, the function just picks up the value of the delta. So let me choose this delta function. This sets q to be t1 minus t3, right? Because this has to be 0 whenever they're not equal. So then q is set to t1 minus t3. So basically, doing the integral just means everywhere you see q, you sum q over. So and your last expression shouldn't have q in it. So you set your q to p1 minus p3. That's how you behave it. So that you do, right? So you expand out this thing, you have ID squared. You get I here. So one of the factors of I multiplies out, you get a 1. And then instead of q squared, you have q1 minus p3. This stays the same. And you have this delta function array. And one of the two flight to the 4 factors has gone away. So this thing, basically, there was a q here. So this is p1 minus p3. You set to there. So this basically accounts for the total energy momentum series. P1, P2 comes in, P4, P3 goes out. Okay, so whatever comes in goes out. So energy momentum is conserved. And this final probably just erase. Just forget about. It's not so simple when you do multiplication. This is just particle picture. So you erase it. So once you erase it, what you're left with is you multiply another factor of minus height with, and you get the amplitude. So this is your amplitude. The amplitude is this real number. Okay. So you notice that this is actually just enough, and that it's algebra. Right. But we're not done yet. I hope you're having fun. This is quite easy to do, and this is quite nice to look at as well. But we're not done yet because I could have labeled this to be P3 and this to be C4. So that we die another diagram. So A1, A and A come in, but okay, they interact via C, but then they may not give you directly B here. Then this may go that, and the other one may go this way. So this cannot happen. So this is not an interaction perfect. Like it's basically an overlap. So if you were drawing circuits, you know, and yeah, but this is not a burget, right? Must be clear. So again, you do this very similar calculation, but all you have really done and basically switch P4 and P3, or P4 and P3 interacts with. So now P2 interacts with P3 and P1 interacts earlier. So I don't need to do the full calculation. Able for you to do it, and then you get another process. All you are doing is really P1 minus P3 just become P1 minus P4 because there's just interchange P1, P3 and P4. Right? So then what is the total scattering amplitude? Now we are done. We just added. And adding and subtracting, you're right to do. Okay. So this is your total amplitude. So from here, we can measure the probability of scattering, which is absolute squared of the amplitude. Right? This is how you do I in and out. Is this a Lorentz scalar function? Because that's important. Every amplitude we calculate has to be Lorentz invariant. Our theory is Lorentz invariant. So is this a Lorentz invariant quantity? What do you think? As I said, it's a number. So by definition. Okay. So whatever amplitude you calculate must always be true that it's a Lorentz scale. Yes. All right. Now we might also have, so these diagrams, these are what we call tree level diagrams. They look at tree branches. spreading out. These are tree-level diagrams. But the ones with the bubbles in here and whatnot, those are called higher order diagrams. And we had higher order diagrams where you go 1, 2, 3. And for example, we have 5 self-energy diagrams. Self-energy is basically a bubble like that. Basically, a bubble in interaction inside internally. And you have 5 of these. You can have 5 bubble wherever you put the bubble in. Put the bubble here, or here. So 5 of these. Then you have 2 vertex direction diagrams, which is basically that 2 triangle diagrams. So we can have 2 interaction vertices here. You can have 2 interaction vertices here. So there are 2 tangent diagrams that look like that. And then you have also a box diagram that looks like box. This is one box that you can make. Basically, you can make a box out of this property. So instead of this one line, you can have 1, 2, 3, and 4 lines. Incoming and outgoing are the same. But as I said, anything can happen here as long as it's exclusively perpendicular. Okay? So you have one box diagram. So these are higher order diagrams. These are going to be important when you actually measure scattering amplitudes and measure scattering cross sections, particle clusters. But the higher order the diagram is, the number of loops you have in a diagram, the number of boxes you have in a diagram, that's more the contribution to amplitude. So basically, it's state to cut off at some point and not do catch space for infinite number of finite lines. So this one of the self-energy diagrams, this is one in the middle. Okay, so we can calculate or a kind of diagram by using our finite restrictions. It's actually the same. You just have more internal lines. So we have 4 integrations: 1, 2, 3, and 4. In other words, you have 2 coming in, you have 2 going out. Inside you have 4 integrations. That's the modification. But all other rules are exactly the same. So I'm not going to repeat them. You have 4 vertices, so you have 4 factors. So how many vertices? 1, 2, 3, 4. Yeah, you have 4 vertices. You have 4 factors of IDs before. And then 4 delta functions because there are 4 internal lines. 1, 2, 3, 4. And for each internal line, you have a denominator which looks like. So then you integrate over all of your internal lines. You have 4 integration variables. So you have 4 factors of 2 pi over 4. But that also cancels out the 4 factors of 2 pi over 4, the delta function. So that's good. And then the integrations are very simple because even if you have 4 gigantic looping integral, they're not very difficult because we have delta. So let's say use this delta function first. This sets Q1 to T1 PG. So this integral goes away. And then let's choose this one. This sets Q4 to T4 minus T2. So this integral goes away. You can keep doing it for the third integral. This one sets Q2 to Q1 minus Q3, but that you have already basically incorporated what Q1 was. So Q1 minus T3 minus Q3. So that you can put in here. All you have that is an integral over 4. Right? So, but that also is set by your last delta function because you have now integrated everything else. So your amplitude then becomes this number. Make sure to incorporate all of these, like check these yourself. The amplitude just becomes this number and remaining integral over Q. And this Q is nothing but Q3. So we have not really officially done this delta function. This interval yet, Q3. This delta function was automatically accounted for by the other. So we have one integral remaining over Q8. Okay. So how do we do it? We apply polar coordinates and we find something variable. This integral is divergent. So this vacuum diagram is divergent. The amplitude is infinity. It's logarithmically divergent. So that's not mine. But Feynman attack again, quite crudely said that include a factor of a fudge factor of this looking kind inside that integral. What are these big lambda? These are just cutoff energy and that. So basically, again telling me to cut off the periods of my energy, right? So that leads me to the fact that you notice that whenever lambda goes to infinity, lambda goes to big, you apply L'Hopital rule, and you see that the fudge factor f goes to 1. So that forcibly makes that finite. So this is the idea of renormalization, how to make entities go away. So not as simple. This is again a very toy model thing. Basically, have to do boundary ratios and whatnot to actually incorporate the finite aspect. But this is the basic idea of renormalization. How you brushing through heat under the rug. So introduction of F leads to the separation of the entity to a finite term and then you will over a logarithmic divergent term, which depends on your energy power, right? So then the finite term sign will give you that. But then this has some important contributions that cannot be ignored all the time. And actually, these kind of amplitude, these terms, we kind of affect what we measure at the collators, the masses, the physical masses, and the physical coupling. So these delta n and delta d are the contributions from this interval, which is logarithmic divergent. And this basically can blow up as lambda gets too large. However, Simon says we are fine because none of us has ever measured any utilities at any laboratory. So essentially, what it boils down to is that we measure m, that is pi, so we can just ignore delta n, whatever they are. So we continue our theory as long as they're finite, and then we throw the infinity away because we never really measure each m's and d's. Okay, but you see the problem with it. It's like brushing things under the rug. Other side of it's not really elegant, but it works. Finite terms from loops I have also contribute to Menchi. And that's where these on is starting. And loops arise from these lambda dependent or MAD dependent terms. This tells me that the higher the energy, the bigger this composition may become. So basically, and for effective masses, the one you really measure, the masses actually start running from the high scale down to the scale where you measure. So masses are not really constant. They run with the energy. They depend on the energy scale that they're making the measurement. Right? So these running of couplings and masses are governed by what we call the renormalization group equations. But that's the idea that the masses and couplings are not really constant. They run with the energy, and you choose the energy to cut it off to extract the mass. So this is basically sweetening 3 Ks under the run by cutting off your at finite energies, and this is the idea of renormalization. Okay, and QE, quantum electrodynamics, quantum chromodynamics, QCD, the scattered model, the Abdus Salam Feinberg model of electronic theory. These are his theories that we know are renormalizable. What does that mean? It means that we can brush infinity under the rug without really affecting the outcome of results. So we can measure these accurately by predicting them, and we have done so, WCs and AIDS and whatnot. However, these are therefore called renormalizable. So we can extract information out of a renormalizable fields. However, if you have the same QFT paradigm that you include gravity in it, then things break down. So gravity, we say it's a non-renormalizable theory in a quantum field theory set. Okay, so for a consistent quantum field theory of gravity, you need to combine general relativity with quantum field theory, and that is the topic that Rapping probably discuss tomorrow or day after. String theory. That's the one best theory that we have for quantizing gravity. Anyone says loop quantum or the loop. So these are non-renormalizable. Right. So I think I will stop here before my next lecture. So